Hi, this time we're going to see what happens with the shear stress. We want to find where are what's the maximum shear stress or maximum shear stresses that we will find in any state of stress. So similarly to the case of the normal stress, if we want to know where are the maximum values of this shear stress here, one thing or the first thing we have to do is to find the solution of the derivative of this function and equal that to zero. Well, basically, find the derivative, equal that to zero, and then find the solution of that equation or remaining equation. So if we do this, we're going to have that the derivative of yeah this term here. I'm going to write down in here derivative of this tau x prime y prime because is the shear stress in an inclined plane with respect to theta. That's going to be equal to, if I kind of make a derivative of all of these, that's going to give me something like, let's see, yeah, this is sine. Yeah, I'm going to try to do it at once. Minus, minus, so okay. So this is going to be, uh, that is, yes, sigma x, x minus sigma y, y. Yes, cosine of 2 theta plus 2 times the shear stress times the sine of 2 theta. And we said that if we want to find the maximum or the maxima, we need to equal this to 0. And in this case, we will notice that for the condition of pure or shear maximum shear stress, it's not necessary that it's going to be 0 normal stress. As in the case of for the maximum normal stress, we found that there is kind of 0 shear stress. Then similarly to the case of the normal stress, the second or next step we have to do here is to find the solution for this equation. And that was basically to find out what was the angle which make, or the angles which make this equation 0. One of the things that we did previously was to find kind of the solution of the angle in terms of the trigonometric functions. And in that case, or to this case, is going to be something like tangent of 2 theta is going to be equal to minus normal stress in x minus normal stress in y divided by 2 times the shear stress, the element. Great. Again, for this case, we're going to have two angles that are going to be separated 90 degrees apart that are going to be the solution for this equation. So we're going to have one angle that's going to be the solution, a random an angle that is going to make this equation equal to 0. And the second angle is going to be one angle that is going to be separated 90% apart. So this pi plus the angle. So in this case, it was written kind of in the previous form. It was written that that angle was going to be something like, we just want to try to write it in the same fashion. The previous time was that the solution for this was going to be found at an angle tangent of 2 theta and also you have to put something here, kind of not to say that this is equal, tangent to pi plus 2 theta. Great. Also, as we know that we found this relation that is going to make this equation 0, one of the tasks that we would do, or we would have to do if we want to go from here to the equations showed, or the equation showed in the textbooks, is that we have to substitute this cosine of theta and this sine of 2 theta using this relationship here as we did with the normal stress. So for example, for the normal stress, we said that sine of 2 theta, I could define it in function of the tangent of 2 theta in this way. And for the cosine of 2 theta, for the normal stress, I said that it could be defined in terms of the tangent of 2 theta in this way. Of course, the values for the cosine of 2 theta and sine of 2 theta in the shear stress case is not going to be the same, so we have to calculate it again, but I won't do it. I will leave it to you to exercise this part. When you find this relation between the cosine of 2 theta, sine of 2 theta with the tangent of 2 theta, and substitute that equation, those two results in this main equation, you will end up with equations found on the textbook. And that equation is something like this. It says that the maximum shear stress is going to be equal to plus minus square root. This is a fine kind of derivation. The subtraction of the two normal stresses divided by 2. This is here. Plus the shear stress of the element. But this is just to say, or this is going to be equally to say that after a few substitutions seeing what is inside of that, this is going to be equal of 1/2 of the subtraction of the two principal stresses found before. So, and this is totally aligned with what what Mohr's cycle has to say regarding what is the value of this. So this is in fact the radius of the Mohr's circle. And you will always find that this Mohr's circle, that the radius of the circle is going to be equivalent to the maximum shear stress. And from other pieces of information, you're going to find that the center of that circle is going to be calculated by the sum, or kind of, yeah, the average of the sum of the stresses of the element. Meaning that if this is the radius of the Mohr circle, then the center of the circle is going to be located at a distance, of course, in the axis related to the normal stresses. Center of the circle is going to be equal to 1/2 of the sum of the stresses in the element. So you see that this is a combination of kind of stresses in the element and principal stresses found, specifically principal normal stresses. Let me mark it down like this one here. Yeah, this is the radius and this is the center. Then I guess we're ready right now to draw the Mohr's circle. And let's put it in this way, that initially the Mohr's circle was thought to be used as a visual aid to determine which were the maximum principal stresses or maximum normal stresses and maximum shear stresses. However, as we have determined many of those quantities, then it is, let's say, it's not redundant to draw the Mohr circle, but it is important also to find somehow what are the angles where those principal stresses are found, because we have derived until now what are the values of the principal stresses and principal shear stress, but we don't know in which angle are they acting. So in the next video, what I will do is to present the procedure to draw the Mohr circle in 2 dimensions, and after that I will present the procedure to draw the Mohr circle in 3 dimensions. And the idea of doing all this recap about the 2D Mohr circle is kind of to put into perspective what was needed to construct these circles. When you migrate from 2D to 3D, it's a little bit, well, not a little bit, but more work, to find out what are these quantities, but the procedure is the same. And the idea is to have kind of the background so a Mohr circle in 3D doesn't come as a kind of a stranger. So it's pretty simple. The concepts are pretty easy to digest, and the idea with this recap was that kind of to have a solid foundation about what's going to be done with the Mohr circle in 3D, which would allow us to continue to comment on the failure theories applied to materials, which are based on principal stresses, principal normal stresses and principal shear stresses. Great. See you in the next video. Thanks.